Okay, now moving on to the next presentation. This is coming from Fangqing Gao, who is a director of new technology development at leading paste maker DKEM. And Fangqing is going to talk about milestones in metallization, advances in silver paste for establishing metallic contact across cell architectures. Fangqing, the floor is yours.
Okay, thank you, Sharon. Thank you for your invitation. I'm Fangqing from DKEM, and today I will introduce the latest metallization solutions for TOPCon DC from DKEM. And this is actually the latest product portfolio of DKEM. Actually, you can see our products almost covered all kinds of cell architectures from PERC, TOPCon, BC, HAT, and also we developed the module interconnection and module encapsulation materials for PV modules. And actually, in this year, we introduced our latest product of the silver lean and the silver free products to help this industry to further reduce the cost of the silver and to reduce the consumption of the silver. And today, my report will focus on the TOPCon and the TBC part and introduce how we increase the efficiency of these kind of cell structures and to reduce the cost. Actually, from the past several years, with the help of the LECO process, the cell efficiency of the TOPCon increased significantly, especially the genome metal of the front side and the total contact at both front side and rear side get greatly improved. And actually, in the past 1 year, still the TOPCon efficiency is still increasing. And a lot of new technology are incorporated in the TOPCon cells, like EPD and polyfinger, 𝐦𝐨𝐫𝐞. This kind of process actually further help to lower the genome metal of the genome of the total cells and also improve the contact, as well as raise the new requirement for the cells for the pastes at both front side and the rear sides. No matter about the genome metal or the reliability and the etching windows at the rear side, these all needs a paste to cooperate with our customers to further improve the cell performance. And actually, at DKEM, we are the first paste vendor that help a customer to put this kind of we call TOPCon 3.0 process that integrated the EPD, polyfinger, and 𝐦𝐨𝐵𝐵 into mass production, and help the TOPCon modules to reach module power output to more than 670 watts. And actually, for the TOPCon front side, even though with the LECO process, actually the VOC increased by more than 5 millivolts, but actually that's not the end. We are still helping our customer to increase the VOC performance by adopting the low-edge weak etching system, especially for the glass freeze tuning to form the lower etching at the front side to boost the higher efficiency. And our customer actually they are also optimizing their emitters and to push the R-sheet to a very high level. Actually, most of our customers, their R-sheet of the front side emitter can go to more than 300, and some of our customer goes to beyond 500 ohm square. Usually, our customer will choose the to a shallower emitter and slightly lower surface doping to form such kind of high R-sheet emitter. Actually, this not only requires the paste to have a very wide contact window, but also need to perform a better, wider etching capability window to ensure that there won't be any over etching performance, especially at the edge of the cell, especially when the R-sheet goes to more than 500. If the etching window of the front side glass is not wide enough, there might be some dark EL issue at the edge. And also, actually, with such kind of low etching, weak etching system combined with the higher sheet performance cell emitter, still we can get more than 1 millivolts, enhancement on the VOC, and as well as maintain the contact and stable FF performance. But worth noting that with such a kind of weak catching system and this kind of high VOC glass-free system, there might be some issue, just like the dark EL at the edge, and also some peeling off issue and some reliability issue that may raise for this kind of glass frit. We need also to optimize the glass frit recipe to balance this kind of performance when we reaching the weak etching system. And another way we help our customer to improve the efficiencies goes to the ultra fine line printing. Actually, that's always a hot topic for the cell front side, no matter it's PERC or TOPCon. Actually, when it goes to the LECO process, there's a wider room for us to go to even narrower finger line openings. Actually, in the past several years, our customer greatly reduced the screen openings of the front side. They go to maybe 1 year before, the screen opening is still more than 10 microns. But in the past year, most of our customers reduced the finger openings below 10 microns. And some of our customers actually goes to below 7 microns. And if we looking at the future, there's a great chance for the screens to go to more than below than 6 and 5 microns, because actually we are cooperating with our customers to try the 4 microns screens, and there's no printability issue right now. The only issue is that the laydown is too low, and there might be some reliability risks for such kind of low laydown. So we believe that with the improve of the glass frit system to improve the reliability, and also the powders and the vehicle can collaborate together, and there's a great chance for us to adopt such kind of maybe 4 to 5 microns printing in the next year or next 2 years. At the same time, actually, this stencil is also a very promising process to approach the fine line. And maybe right now there's still some lifetime issue or some appearance issue for the stencil, but our partners, like the stencil vendors and our customers, they are working on the pattern design, they are working on the screen process optimization to solve such kind of lifetime and appearance issue. And actually, in the past year, several customers also run the stencil in mass production. And because of the better morphology and narrow fiber width, there's a great chance for the stencil to achieve more than 0.1 efficiency gain. PTP maybe right now is facing great challenge from the PI screen and the stencil, but still we can see that if we're looking at the future, the fiber width of the PTP still have great advantage than stencil and the PI. Maybe the only issue is to solve the cost of this such kind of process. And for the TOPCon rear side, actually, with the LECO process, the contact at the rear side also got improved. So with our latest rear side paste DKE95E, we also utilize such kind of effect from the LECO at the rear side to form that we will also weaken the etching capability of the rear side glass frit to form the low etching system. And we reduce the etching depth, and at the same time, we improve the density of the silver nanocrystallize to form a better contact, as well as to reduce the genome metal. This actually works when a customer goes to a narrower poly thickness. And actually, there another way to reduce the poly thickness is the poly finger, and especially for LP process, because the LP process is difficult to reduce the thickness because of the when you go to thinner poly, there will be very high challenge for the contacts. But polyfinger can solve that issue perfectly. And the only issue is that usually our customer, when they go to the polyfinger, and they will adopt the full side aluminum oxide at the rear side. So for paste, we have to etch through the aluminum oxide first, and then form the contact. That's raises a requirement that we have to perfect etch through the aluminum oxide and make sure that we don't etch through too heavily that damage the polysilicon. So for the rear side, with the polyfinger process, it needs wider etching window of the rear side finger paste. And for the rear side paste, another issue is that the printability, especially when the lay down the rear side goes to a very low level. The morphology actually plays a very important role to maintain good contact, especially when our customer they are in mass production, they will frequently change the switch or change the screen. If the paste transfer or the morphology of the finger is not so good, there will be an efficiency drop when they doing such a kind of changing switch or changing screen. So the morphology and the pitch transfer must be good enough to ensure that the contact will not get compromised when they're doing such kind of actions in the mass production. So morphology actually plays a very important role for the rear side finger in right now at the current stage of the TOPCon rear side. And that's the TOPCon actually for TBC, the very hot topics right now. A lot of customers they are considering to upgrade their lines to a TBC cells, and some of our customers actually they have run TBC production line for a long time. Actually, right now the process of TBC is relatively stable, so our customer put a lot of resource on the paste development to help to improve the efficiency of the TBC. Usually for the TBC, the p-poly contact is always a very difficult point to very difficult thing to form the good contacts because of the natural features of the p-poly. Usually, in the past several years, we have greatly improved the contact of the p-poly, and actually the contact resistivity of the p-poly now is even lower than the TOPCon frontside emitter. We have to form a very actually very dense silver crystallites to ensure the good contact, and also reduce the size of the crystallites to maintain the good J-non metal. At the beginning stage of the TBC, usually our customers' p-poly thickness is very thick, so we can increase the etching capability to maintain a good contact. But right now we have to notice that a lot of customers, their poly thickness is quite thin. Some even goes to below 250 nanometers. So we have to balance the etching capability of the glass bridge to maintain a good J-non metal, as well to improve the contact. That also comes to the next topic, that is the cost reduction of the TBC. Actually, related to metallization, there will have two ways to reduce the cost. One way is to cooperate with customer to reduce the thickness of the polysilicon. Actually, when customer reducing their thickness of the polysilicon, there will be a higher requirement for the paste to contact the silicon, especially for the p-poly, because the R-sheet will raise rapidly for the p-poly. And also the J-non metal will get very sensitive. So when the customer goes to below 250 nanometers, if they don't change the paste, usually they will experience that the VOC and the FF will drop rapidly, especially for the P-poly. So we have to optimize our paste to reduce the size of the silver crystallites and also to increase the density of the silver crystallites to maintain a good contact as well as to reduce the damage to the polysilicon. And actually with the process optimization and with the upgrade of the silver paste, we can help our customer to reduce the thickness of the N-poly to 180 nanometers and reduce the P-poly thickness to 200 nanometers. And I believe there's still some room for the poly thickness to further get reduced. That will be the job for us and also for our customers. And in the past years, actually, another way to reduce the cost, actually very significantly way is to adopt the stencil screen for the TBC. Our customers, when they adopt the stencil on TBC, there will not only be the paste saving, but also help to improve the efficiency, because actually for the fingers, the efficiency is very sensitive to its uniformity. And then stencil not only form a very narrow finger, but also help to optimize the uniformity of the finger morphology. So that's help our customer to improve the efficiency as well as to reduce the lay down of the silver paste. And to further actually to reduce the cost of the silver paste, we have to consider some other cheap materials to replace the silver. And there are several choices like copper and aluminum and maybe nickel. But if we looking at the basic features of the copper, basic features of the metal and the cost, actually copper is still the first choice to replace silver, because the resistivity of the copper is similar to silver, and it has a wide adoption actually on the electronic industry already. But to adopt copper on TOPCon or TBC cell, there will be several challenges for the copper. And the one thing is that the oxidation, we have to incorporate some anti-oxidation concept in both of the copper powder and also the copper paste, even at the firing process and at the encapsulation stage. And another thing we have to solve is a firing process, because the fire of the copper paste is very sensitive to the oxygen. So the atmosphere and the firing temperature, the time, actually that all matters. That all matters to low resistivity of the fired green line, and also the pressure, and also some other process like laser firing. We are also considering such kind of process that help to adopt the pure copper paste to the current PV cells. And another issue is the copper diffusion. That is highly related to the reliability of the cell. Actually, our customer care a lot about this kind of issue. For HJT and HBC, such kind of low temperature process, there will be TCO as a natural barrier to resist the copper from diffusing to the silicon. But for TOPCon and TBC, because we have to form the contact first, so we have to damage the passivation layer first to form the contact. That means that there will be a.
You have one more minute to finish.
Okay, then I will go to the next page. That's the solution we offered for the TOPCon and TBC. We use ultra low silver content C layer as to form the ohmic contact from with the silicon, and we use a high copper paste to form the as a second layer to form a transportation layer, and such kind of process actually we already put it into mass production with our customers, and the cell and the module reliability also passed. And actually, that is the first mass production case of the high power paste in TOPCon. We help our customer to greatly reduce the cost of the silver. And right now, we only adopted this kind of process at the rear side of TOPCon, but there's a great chance to adopt that also on TBC. And we are trying some new solutions for the TOPCon front side. Okay, that's a report of mine. Thank you, Sherman.
Thanks a lot, Fangqing, but you have used your time. Even I have few questions. Maybe I will also post in the chat window. Well, meanwhile, I would like to move to the next presentation. Thanks a lot. It was really interesting presentation.
Okay, thank you, Sherman.